Hello, everyone. I hope you all are doing good. I'm Diptak Bhattacharya. I am a graduate student in the MMA department of Colorado School of Mines. The title of my presentation is Influence of Chemical Composition on Liquid Metal Embrittlement or LME Sensitivity of Zinc-Coated Advanced High-Strength Steels. I would like to thank all my advisors, Professor John Spear, Professor Kip Finley, Professor Lawrence Cho in Colorado School of Mines, and all my industrial mentors from different automotive and steel companies for their continuous support and enthusiasm in this project. Now, this problem of liquid metal embrittlement has surfaced very recently, but it's of huge concern to the automotive industry that relies so much on advanced high-strength steels at the moment. So let me first tell you what is liquid metal embrittlement. Now, in all advanced high-strength steels that are used in the automotive industry, we apply a zinc coating on the surface of the steel to prevent the steel from corroding. Now, if we have a zinc-coated steel, as I told you, the zinc coating is on the surface of the steel. Now, if we heat the zinc-coated steel to a temperature above the zinc melting temperature, we will have liquid zinc on top of our solid steel. Now, in that condition where liquid zinc is present on top of our solid steel, if we simultaneously apply a tensile stress, then what we see is that the liquid zinc from the coating starts to penetrate into the steel via the grain boundaries of the steel, weakening the steel, giving rise to surface cracks. So here is the SEM and corresponding zinc EDS map from the longitudinal cross-section of a zinc-coated steel that was deformed in tension at a temperature above the zinc melting temperature. So here is a zinc coating, that's the steel, and the zinc EDS map tells us that the zinc from the coating has penetrated into the steel, so that's an LME crack. Now, in the past 4 to 5 years, different researchers investigated the LME susceptibility of the different steels that are available today. So here is a conventional strength ductility or the banana diagram showing the various families of steels that are present in the market today. And here are the various researchers that investigated the LME susceptibility of these different families of steels. And one clear outcome of these investigations has been that it has clearly shown that the recent generations of advanced high strength steels having a strength level of above 1 GPa with exceptional ductility, these steels are more LME susceptible compared to the Gen 1 AHSS and the other steels that are available today. And some of these advanced high-strength steels that were developed right over here in Colorado School of Mines, but we clearly don't understand what induces the high LME susceptibility of these steels, because every steel in this list has different microstructure, different chemical composition, and both microstructure and chemical composition can independently influence LME susceptibility. Now, in my previous grads presentation of 2020, I showed you how the microstructure of these Gen 3 advanced high-strength steels can independently influence LME susceptibility. So in this presentation, we will have an answer to another important question as to whether the chemical composition of an advanced high-strength steel can independently affect LME sensitivity. Now, how do we have an answer to this difficult question? Now, carbon, manganese, silicon are the three main alloying elements that are present in AHSS. So what we thought is that we are going to individually vary the carbon, manganese, and silicon contents in the AHSS substrate. Then we are going to generate a similar substrate microstructure so that microstructure do not affect the results of our experiment. Then we are going to apply a zinc coating, and then we are going to test the LME sensitivity of these steels of different chemical compositions. So we had 4 experimental steels. We had the base alloy having the highest concentration of carbon, manganese, silicon, typical AHSS composition. We had a low carbon variant having a lower carbon concentration, manganese and silicon remaining the same. We had a lower manganese variant having lower manganese concentration, carbon and silicon remaining the same, and we had a low silicon variant having low silicon concentration, carbon and manganese remaining the same. And in all these 4 alloys, we generated a similar microstructure via quenching and partitioning, so martensite and wheaten austenite in the microstructure, a typical 3rd generation AHSS microstructure. It would be very interesting to see how the LME sensitivity can vary based on the varying alloying concentrations in these different alloys. But before we test the LME sensitivity, we have to apply a zinc coating. So we electroplated zinc on the surface of these steels, and then we performed hot tension tests at temperatures above the zinc melting temperature. So this is our hot tension test cycles. We performed our hot tension tests at different temperatures above the zinc melting temperature. And in this presentation, I will show you the results of hot tension tests at one temperature, which is 700 degrees C. So let us see. The next slide has the big reveal. So zinc-LME susceptibility as a function of AHSS composition, we see that the base AHSS having the highest alloying content, the low carbon AHSS, the low manganese AHSS, all crack to similar extents. So likely the carbon content or the manganese content of the AHSS does not affect LME susceptibility. On the other hand, the low silicon AHSS have little to no cracking. So we instantly understood that the silicon content of an AHSS independently influences LME susceptibility. Now, this is so interesting. When we have a high silicon AHSS, the fracture surface of our zinc coated specimen is clearly indicative of a brittle intergranular failure, so typical LME failure. When we have a low silicon AHSS also coated with zinc, the fracture surface of the zinc coated specimen is clearly indicative of a ductile failure. So now in order to understand the science behind this behavior, we have to go back to the basics. Now, what are the criteria that are required to trigger LME? First, we need to have an abundance of liquid zinc, and importantly, the liquid zinc must be in contact with the steel. We need to have a susceptible microstructure, and we need to have a tensile stress. Now, we had a susceptible microstructure in all these alloys. We applied a tensile stress to all these alloys. So these two criteria cannot explain our behavior, our observed behavior. So likely the behavior we observed can be explained in terms of how the liquid zinc interacts with the low silicon or the high silicon substrate, which directly controls the abundance of liquid zinc and whether that liquid is in contact with the steel or not. So let's see. Now we looked into the microstructure in the coated region of the high silicon containing AHSS after hot deformation at 700 degrees C. So here is the backscattered electron micrograph showing the outer layer, which is the coating, and the inner layer, which is the steel. In this case, the coating only comprised of the solidified liquid zinc. Therefore, we know that in the case of the high silicon AHSS, we started with a pure zinc coated sample at room temperature. We heated it up to high temperatures. The zinc melted. We had liquid zinc in contact with the high silicon substrate so that upon applying a tensile stress, the liquid zinc penetrated into the steel. So typical LME as we think about. Now, in the case of the low silicon AHS is deformed at the same temperature, here is a backscattered electron micrograph from the coated region. So the outer layer again is the coating and the inner layer is the steel over here. There is solidified liquid zinc on the outer side of the coating, but on the inner side of the coating, right next to the steel substrate, there is an Fe zinc intermetallic layer, which is a solid layer that formed by the reaction between the liquid zinc and the steel substrate. So what happened in the case of the low silicon steel is that we again, similar to the high silicon steel, we had a pure zinc coated sample to begin with. When we heated to the high temperature, the zinc melted, immediately reacted with the low silicon substrate to form an Fe zinc intermetallic layer. The intermetallic layer consumed a part of the liquid and prevented the direct contact between the liquid and the steel, so that when we applied the tensile stress, there was no LME. So therefore, we believe that silicon affects the way the liquid zinc reacts with the steel substrate. So the big question now is, does silicon addition to a steel suppress the intermetallic formation behavior? Let's see what thermodynamics has to say. So first we look into the Fe zinc binary phase diagram. So a situation where we have liquid zinc in contact with pure iron, no silicon. So we look into the zinc-rich side of the iron zinc phase diagram, and at 700 degrees C, the phase diagram tells us that two phases are at equilibrium. You can have liquid and you can have the gamma Fe zinc intermetallic phase. Now let's see what silicon addition does to the relative stability of this gamma phase and the liquid phase. Now, we can no longer now refer to the Fe zinc binary phase diagram. Rather, we have to go to the Fe zinc silicon ternary phase diagram to understand what silicon addition does to the Fe zinc system. So here is the isothermal section at 700 degrees C from the Fe zinc silicon ternary phase diagram. And if we consider an alloy having, say, 20% iron, 80% zinc, that is represented by that point on the phase diagram. Now, if we add intentionally silicon to this alloy, keeping the Fe zinc ratio fixed, and we look into the relative stability of the gamma phase and the liquid phase, here is the result. We see that the gamma phase stability reduces as we increase the silicon concentration of the alloy with a concurrent increase in the liquid amount that is present at equilibrium. So as we increase the silicon content of the alloy, we reduce the intermetallic phase stability, we increase the amount and stability of the liquid. So that's what thermodynamics also tells us, which backs up our observation that we had from our coating microstructural study, which also explains why the low silicon and the high silicon steel had different liquid metal embrittlement behavior. So in conclusion, chemical composition can definitely affect LME sensitivity, as we had seen in this presentation. LME sensitivity strongly correlates specifically with the silicon content of an AHSS. High silicon content leads to more LME. We didn't find a correlation with the carbon and manganese content of an AHSS. Silicon influences the substrate coating reactions and intermetallic formation behavior at high temperatures. Recall those coating microstructures that I had shown you. And in the low silicon AHSs, we saw that the liquid reacts with the substrate to form an effusing intermetallic layer that provides a solid barrier between our liquid zinc and the steel substrate that helps suppress liquid metal embrittlement. So thank you very much. And if you have any questions, please feel free to email me at this ID. Thank you so much.